All right, section 25.3. The last thing that we are going to discuss with organic compounds is functional groups. And here's the thing with functional groups is in exposing you to functional groups, I want to just give you an idea of what the names of our functional groups are. So we've talked about alkenes, alkynes. We've talked about how they work. What I want you to get familiar with is the rest of this list. And yes, you are going to have to study this list and understand this list from an organic compound standpoint. We've talked about alcohols before with OH. We haven't really talked about ethers. A haloalkane is simply an alkane that's replaced with a halogen, such as chlorine, bromine, fluorine. An amine, such as ethylamine, means that we have a nitrogen group substituted for one of the carbons. Our prefix is amine, ethylamine. Ethyl, because we have two carbon groups. An aldehyde is a double bond with an oxygen and AH. So, for example, our endings are all L, AL, not all like alcohol, OL. They're aldehydes, they're ALs, AL. So here we have ethanol. Right. Ketones is simply, ketones are just double bonds. Ketones is a double bond with oxygen, so we have 1, 2, 3, 3 carbons. So we have, instead of propane, we're going to have propanone. All right, propanone. And you can kind of see down here is the list. Now let's highlight the common groups. Alcohols contain one or more hydroxyl groups, so they contain an OH. So 2-propanol, 1, 2, 3. We have 3 carbons, an alcohol group here, an OH, so we have 2-propanol. This is known as isopropyl alcohol or rubbing alcohol. Here we have two alcohol groups. So we have 1, 2. Our group here, we have single bonds, so it's ethane, but now it's ethane diol because we have 2 alcohol groups. So 1, 2, ethane diol. That's also known as ethylene glycol. We have cholesterol as an alcohol group, and these molecules get bigger they go. They are named simply because with OL. Alcohols are much more acidic than hydrocarbons. Their pKa's are quite large. And aromatic compounds have a pK, alcohols have a pK around 10. Ethers. Ethers tend to be very unreactive. Therefore, they make great polar solvents, and ether is when we have an oxygen bonded between 2 carbons. So we have a diethyl ether here. Why do we have diethyl ether? Because we have an 2 carbons on both sides here, so it's diethyl ether. You can see the ether works as well here. Carbonyl compounds. Right? Typically, there are a couple of them. We can have an amide, which is a nitrogen bonded to a carbon. We can have an aldehyde, which is a oxygen double bonded with an H. We can have an ester, which is an oxygen double bonded and then single bonded with an oxygen bonded to something else. Our carboxylic acid, which is COOH, or a ketone, which is a double bond and then something else bonded to it. These R signify our carbon chains. These R prime signify something else that could be bonded to it, such as additional carbon chains. So aldehydes, here you go, very simple aldehyde. We have a double bond with carbon. We have 1 carbon, so instead of being methane, we're going to end with the prefix methanol. This is commonly more known as formaldehyde. Same thing here. We have 2 carbons, so rather than being ethane, it's ethanol or acetaldehyde. Ketones. Ketones is when we strictly just have a double oxygen or oxygen double bonded. So we have 1, 2, 3 carbons. Instead of being propane, it's going to be propanone. Its common name is acetone. All right, 1, 2, 3, 4, 5, or excuse me, 1, 2, 3, 4 carbons. We have 4 carbons, so this would be butane, except we're going to note where the double bond is for with oxygen, so it's going to be 2 instead of butane, butanone, and this is also known as methyl ethyl ketone. Carboxylic acids are when we have a ketone with an alcohol group, essentially. So we have an oxygen double bonded with an OH group. They are tart tasting. So a lot of these form acids which are tart. For example, citric acid is probably the tartest of all the acids. I don't know if tartest is a word, but we're going to go ahead and use it. Acetic acid right here, that's vinegar. Aspirin. Aspirin itself is very tart. If you'd ever bitten into an aspirin, it is very tart. So these carboxylic groups are very tart tasting. And you can see here we have 2 carbons. So instead of being ethane, this is going to be ethanoic acid because it's our carboxylic acid. That's known as acetic acid. Here we have a double. Here, let's go up here. We have 1 carbon, so instead of being methane, it'd be methanoic acid. Lactic acid, you can see you have 1, 2, 3. We have a different OH group here. However, they are tart tasting. However, our carboxylic acids are incredibly weak acids. Esters, what we have here is esters are the product of a reaction between carboxylic acids and alcohols. So we have, remember, ethers was an oxygen bonded in the middle. Now we're going to form what we have an ether here with our carboxylic group, and we're going to have a double bond with that oxygen. So esters, kind of byproducts of ethers, they're found in many fruits and perfumes. Amide is when we have that nitrogen group off of our carboxylic acid. So we have a carbon double bonded with an oxygen and a nitrogen. I know we're flying through these really quick, so take some time, slow down, take some notes, really understand what's happening with each of these. So I really want you to understand the group and what it looks like, and we'll kind of maybe, if we have time, talk about how it reacts individually. And we have amines. Amines are organic based. So you can see here 1, 2 carbons. That would be normally ethane, but we have an amine and NH group on the end here, so it's ethylamine. Here we have trimethylamine because we're going to have 3 methyl groups bonded to this end, so trimethylamine. And here we have phenylamine because we have a aromatic compound, our 6-member ring, with an amine group on the end. These are generally strong, have very unpleasant odors. Isn't that the truth? We're not going to go into talk about, actually we'll do this real quick here. Carbons with 4 different groups attached to them are handed, or what we call chiral. What the heck does chiral mean? That means they are optical isomers or stereoisomers. What that means is if I flip-flop them in a mirror, they're the exact image. So right here, this molecule has chirality, which means it's an exact mirror plane. It looks the exact same in a mirror. And this is a 1, 2, 3, 4, 5-member carbon ring. So it's going to be a pentane group, and we're going to have the halogen here. This is a halogen bromine off of that here. Many pharmaceuticals are chiral. And that's where we're going to stop. We're not going to go into any biochemistry. If you do this, exposure to organic chemistry will be good enough for your exposure to biochemistry when you take, hopefully all of you take a biochemistry class in college. So this concludes section 25.3, and this sadly is indeed our last section of the year. This is Mr. Clennert. I hope you've had a pleasure listening to the Flipped Classroom this year. Thank you.